afternoon, class. In today's topic, we are going to be looking at gas mixture. What do we understand by the term gas mixture? A gas mixture is defined as a combination of two or more gases that do not react chemically but have the same volume. An example of gas mixture is air. A mixture of nitrogen, oxygen, or a mixture of carbon and oxygen can give you a mixture. Let's look at a schematic in illustrating this. When we have a mixture of carbon, 4 oxide, this simply gives you by adding carbon and oxygen. When you add these two terms together, you have a mixture of carbon and oxygen. The same thing also applies to air. When you mix nitrogen and oxygen together, you have nitrogen 4 oxide. Now, the next thing we are going to be looking at is the composition of gas mixture. We have two compositions of gas mixture. We have the mole fraction and we have the mass fraction. The mole fraction can also be known as, or it can be analyzed using the mole analysis. This can be analyzed using mole analysis. And the mass fraction can be analyzed using gravimetric analysis. So when we are talking about mole fraction or mass fraction, a mass fraction is the amount of the mass that is present in a mixture of a particular mass. A typical example is, I'm still going back to the example I made use on the board, which is carbon 4 oxide. You want to determine the mass fraction of carbon in carbon 4 oxide. What we are going to do first is this. The mass fraction is designated or represented as M subscript F, and it is defined as the mass of the gas divided by the mass of the mixture. Now, for nitrogen, we have nitrogen plus oxygen gives nitrogen 4 oxide. We want to determine the mass fraction of nitrogen in nitrogen 4 oxide. Let's say, for example, if we have 5 kilograms of nitrogen and we have 8 kilograms of oxygen present in a mixture of NO2, which is around 30 kilograms. The mass fraction of nitrogen that is present in the mixture is determined going by the expression we have here. So we have it as mass fraction of nitrogen equals to the mass of nitrogen divided by the total mass of the mixture. And the mass of nitrogen in this case is given as 5 kilograms divided by 30 kilograms. So the mixture in this case becomes 0.16. Let's take an example. Example 1. Consider a gas mixture that consists of 5 kilograms of oxygen, 10 kilograms of nitrogen, and 15 kilograms of CH2H4. Determine 1. The mass fraction of each component. B. The mole fraction of each component. And C. The average molar mass and gas constants of the mixture. Now, solution. The given data in the question, we are given mass of nitrogen as 10 kg, mass of oxygen 5 kilograms, and mass of C2H4, so it means 15 kilograms. Now, we are going to define the unknown. Find 1. The mass fraction of each component. Mass fraction of nitrogen, oxygen, and C2H4. Also, we are asked to determine the mole fraction of each of the constitution or components. And also, we are asked to determine the molar mass of the mixture, the molar mass, capital M, of the mixture, as well as the gas constants of the mixture. All these are the things that we are asked to determine. They are the unknown value, and we have defined them as this. The next thing we are going to do, according to our problem-solving techniques, is to carry out or state the assumptions in the problem. Assumption 1, under specified condition, nitrogen, oxygen, and C2H4 behave as an ideal gas. The second assumption, the overall mixture is termed as an ideal gas mixture. The overall mixture is taken as an ideal gas mixture. The next is, we start solving. Analysis. The first thing we are asked to determine is the mass of each of the constituent gas in the mixture. The first thing we need to do is we have to determine the total mass of the mixture. Summation of M from I equals to 1 to N, which is the same thing as MT, which is the same thing as mass of O2 plus mass of N2 plus mass of C2H4. Now, insert the value into this expression. So the total mass of the mixture becomes mass of oxygen is given as 5 kg and mass of nitrogen is 10 kg and that of C2H4 is given as 15 kg. So by the time we have all this value, we have 30 kg for the mass of the mixture. We are not yet there. What we are asked to determine is the mass fraction of each of the constituent gas. Now for oxygen, the mass fraction of oxygen is defined as M mass of oxygen divided by the total mass of the mixture. In certain values, we have mass of oxygen to be 5 and that of the total mixture should be what? 30 kilograms. This cancels this. 1 here, 1 in 5 in 30. That is 6. 1 over 6, which is equivalent to 0.16. That is the mass of the constitution of oxygen present in the mixture. Also, mass of nitrogen present in the mixture, N2 equals to mass of nitrogen divided by the total mass of the mixture, which is 10 kg divided by 30 kg. Kilogram cancel kilogram. This is, we have 1 over 3 is 0.33. And lastly, for mass, the mass of C2H4, mass of C2H4 divided by the total mass of the mixture, which is given as 15 kg divided by 30 kg. So we have this here 1, this here 2, 0.5. So we have determined the mass of the constituent gas in the mixture. The next one is to determine the number of moles of each of the constituent gas in the mixture. Now, let's refer back to our fundamentals. Mole is defined as the rate of mass divided by molar mass. Mole equals to mass over molar mass. Now for oxygen, NO2 equals to mass of oxygen 5 and the molar mass of oxygen is 32. 5 divided by 32, 0.1566 units kilomole. Number of mole of nitrogen, mass of nitrogen, which is 10, divided by the molar mass of nitrogen, 28. When you divide them by 28, 0.357 kilomole. Also, the number of mole of C2H4 is the mass of C2H4, which is 15, divided by 24 plus 4, that's 28. So 15 divided by 28 is 0.541 kilomole. Now the total number of mole of the mixture is what we are about to determine now. So we are going to use this expression, summation of N from I equals to 1 to K which is the same thing as NT, is the total number of mole of oxygen plus number of mole of N2 plus number of mole of C2H4. Inserting the values, we have 0.156 plus 0.357 plus 0.54. The total value is 1.053 kilomole. That is NC value. Now, we are not yet there. So we need to go back to what we are asked to determine from the question, which is number of mole of each of the constituents. NF of oxygen equals to N oxygen divided by NT, which is 0.156 divided by the total number of mole, 1.053. The value becomes 0.148. NF of nitrogen equals to N nitrogen divided by NC, which is the same thing as 0.357 divided by 1.053. 0.3339. And the number of mole of C2H4. We have N C2H4 divided by NC, which is 0.54 divided by 1.053. And the value is what? 0.5128. Note, when you have the number of mole of each of the constituents mixture of the gas together, it must give you the total number of mole of the mixture. Now let's go back to the third thing that we are asked to determine, the molar mass of the mixture. Molar mass of the mixture. How do we calculate the molar mass of the mixture? The molar mass, since number of mole equals to mass over volume, so we can easily make molar mass the subject of the formula in this case. Molar mass of the mixture, let me use T for the mixture, equals to total mass divided by total number of mole. And the total mass is given as what? 30. The total number of mole is given as 1.053. So when you divide this expression, what do you have?
28.49.
28.49, which is approximately 28.5. And lastly, we are asked to determine gas constant mixture. So we go back again. Going back to this expression, the gas mixture equals to the universal gas constant divided by molar mass. The universal gas constant is 8.314. 314 divided by the molar mass of the mixture has been calculated to be 28.5. So when you divide this, what do we have?
0.2918.
0.2918. A kilojoule per kilogram Kelvin. So we are done with the problems that we are asked to solve. Relating volume, pressure, and temperature for gas mixture. Pressure, volume, and temperature. Gas mixture. For ideal gas, we have an expression that we normally use for an ideal gas, and that expression comes in the form of PV equals to nRUT, or PV equals to mRT. If you look at these two expressions, they are the same thing. The only thing that makes it different is the number of mole and the universal gas constant. If you look at the second one, we have mass and gas constants. So if you go back to the mathematical expression of N, which is mass over mole, when you substitute it into this, you have this, but that is not where we are going to. What we want to try to achieve now is we made use of a particular value in the just concluded work example, which is universal gas constant. How do they arrive or achieve that value is what we are about to do now. So now let's go by this equation. PV equals to nRUT. Now for a unit mole, the equation becomes PV equals to universal gas constant multiplied by temperature. So making this the subject of the formula, we have PV over T. Now let me take you back to fundamental. In chemistry or physics, they will say volume as STP. STP is known as what? Standard temperature. Temperature and what? And pressure. The standard temperature is 300 Kelvin, which is equivalent to 273 degrees Celsius. 273 degrees Celsius. For pressure, 1.0125 times 10 raised to the power of 5. That is in Pascal. Then for that of volume is 22.4 GMQ. So when we substitute these three values into this expression, let's name it equation 1. So we have the universal gas constant to be pressure is 1.0125 multiplied by 10 raised to the power of 5 times the volume 22.4 divided by the temperature, which is 300. So the final answer becomes 8.314 kilojoule per kilogram Kelvin. So that is how this expression is gotten. Now, from this expression we have on the board, the ideal gas equation, we now be the ones to help us to relate some simple gas law. What are these simple gas law? The first one, the Boyle's law, the Charles law. We have pressure law. We have the general gas law. We have Avogadro's law. Avogadro's law. Going back to the simple gas law that I have just mentioned, we still go back to the ideal gas law, which is PV equals to RUT. Now, We can use a schematic to represent the three major laws that are that are our own concern as an engineering student. So looking at this, we can represent this as ideal law. This is Avogadro's law, the Boyle's law, and Charles' law. Going back to the ideal gas equation, we can reduce some of the terms in this expression. Don't forget that R subscript U is called universal gas constant. Is a constant itself. Now, when we make it as a constant, you will notice that we are left with PV equals to T. PV equals to T. Or going back to that law, RU. When RU is made constant in that expression, we have the general gas equation. We have the general gas law, which is PV over T. So we can generalize the equation so far it is the same thing as the constant as P1 over T1, P2 over T2 equals to P3 over T3 equals to Pn over Cn, depending on the states that you are heading to. If you are considering two states, you stop at 2. V1 over T1 equals to V2 over T2. This one is meant for the general gas law. Then going back to Boyle's law, when the temperature is held constant from the ideal gas equation, which is equation 1, we get another expression which is known as Boyle's law. And don't forget the way the Boyle's law is being stated, that the volume of the given masses of gas at a constant temperature is what? Inversely proportional to the pressure. So therefore, when we have PV equals to constant T, we have Boyle's law. Boyle's law. So we can generalize the equation as P1 equals to P2 V2. This is meant for Boyle's law. But in a situation whereby P is held constant, we have an isobaric process in such case. We are left with what? V over T equals to constant P. So in this case, we have Boyle and we have Charles' law. Charles' law. So we can generalize the equation as V1 over T1 equals to V2 over T2. And lastly, for Avogadro's law. So we go back to the general form of ideal gas equation where we have PV equals to nRT. In this case, the universal gas constant and the temperature, the universal gas constant, the temperature, and the pressure at this level are being neglected. They are held constants. So therefore, we have V over N equals to every other values, which is constant RT over what? P. So we have it in the general form as V1 over N1 equals to V2 over N2. All these expressions that we have just done on the board comes under the ideal gas law. Also, we also have for real gases. For real gases, that is when we'll be talking about the Van der Waals, the Bartop law, and so on and so forth. There are so many of it. The next two things that we are going to be talking about today before we end the class is Dalton model and Amagat model. The Dalton model is talking about pressure, while the Amagat model is talking about volume. Now, let's start with the first one. The Dalton law of partial pressure states that the total pressure of a mixture of gas is the sum of its partial pressure present in the gas. So now let's go back to the ideal gas law expression. PV equals to NRUC. For Dalton's law of partial pressure, let's take a schematic in illustrating this because we are talking about a mixture of different gases. But in this case, we are looking at three gases. This is the mixture. Looking at the schematic that we have on the board, we have gas A, which is represented as circle. Let's say, for example, this is nitrogen. We have gas B, which is represented as diamond, and we have gas C, which is represented as a square. When you mix the three gas together, you have something that we have at the center, which is a combination of gas A, gas B, gas C. So how do we go about this? Going back to the general ideal gas equation to determine the Dalton's law of partial pressure. What we are going to do is very simple. Just make P the subject of the formula. P, which is NRU divided by NRUT divided by P. In this case, the number of moles of each of the constituent gas is our major concern. So we go over it. For the total number of moles, don't forget that we have done an expression that NT equals to NA plus NB plus NC. We go back to the expression. The total pressure of the mixture of the gas is the sum of what? The partial pressure A plus partial pressure B plus partial pressure C. So going back to this, make this expression for A. So we have number of mole of A, RU multiplied by T over V. That is for gas A plus gas B, NB, the universal gas constant, the temperature divided by the volume, and lastly, NC RU multiplied by T divided by V. This is the total pressure that occurs in the mixture following the Dalton's law model. The second one is the Amagat model. The Amagat model follows the same way the Dalton's law of partial pressure. And Dalton's law and Amagat's law are closely related with the ideal gas equation. How do we state the Amagat's law? The Amagat's law states that the total volume of a mixture is the sum of its partial volume present in the mixture. So let me just use a small schematic in illustrating this. We follow the same procedure. We have A. We have B. B. We have C. So we have A, B, C. We have B, A, C, and we have C, D, A. So this is for Amagat's model. And this one is for Dalton's model. So we follow the same pattern that we use in analyzing the Dalton's law of partial pressure. So how do we go about this? We make B the subject of the formula from the ideal gas equation. So we have B equals to NRU C divided by B. So which means the total volume is the sum of what? The partial volume present in A plus partial volume of B plus that of C. So we go back. VT becomes NA RUC over P plus NB RUC over P plus NC RUC over P. So this is the expression for Amagat's model.